Pluto, a distant and perplexing celestial body, was once regarded as a distinct and legitimate planet within our solar system. It was considered a member of the planetary family until recent provocative statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku thrust Pluto back into the spotlight. These renowned experts have made a startling claim. Pluto may be on a potential collision course with Neptune. But how is such an event possible? What could the consequences of such a colossal event be? Are we witnessing a fascinating cosmic anomaly? Or is there more to this impending celestial occurrence than meets the eye? Join us as we delve into the possible repercussions of a Pluto-Neptune collision. Pluto, once classified as a planet but relegated to the status of a dwarf planet, continues to capture the curiosity and attention of astronomers and researchers within the vast expanse of the universe. According to studies by leading space scientists, Pluto's orbit is precariously close to Neptune's. Astrophysicists such as Tyson and Kaku have raised concerns about the potential dangers posed by a collision between these two celestial bodies, which could, in turn, pose a significant threat to Earth. But how could such a catastrophic event unfold? Pluto's orbit around the Sun is unlike that of any other planet in the solar system. It takes a staggering 248 years to complete a single orbit, which means that since its discovery in 1930, Pluto has not even finished one full orbit yet. However, the intrigue does not stop there. Pluto's orbit is marked by an unusual shape, significantly different from the nearly circular orbits of the major planets. What makes Pluto's path so much more unpredictable is its 17 degrees inclination relative to the ecliptic plane, which makes its orbit notably more erratic compared to the other planets. This oddity adds further complexity to Pluto's orbital behavior. Perhaps one of the most captivating aspects of Pluto's orbit is its interaction with Neptune. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, which contradicts our expectations based on their positions in the solar system. This raises the obvious question: why hasn't Pluto collided with Neptune already? The answer lies in the gravitational influences exerted by other planets in the system. The study of Pluto's orbit began soon after its discovery, and initially, astronomers were puzzled by its erratic path. Unlike other planets whose orbits lie close to the ecliptic plane, Pluto's path stood out due to its steep inclination and unusual shape. The mystery surrounding Pluto's orbital characteristics can be explained through a concept known as the three-body problem in celestial mechanics, which seeks to understand the movement and interaction of three objects: Pluto, Neptune, and the Sun, under their mutual gravitational influences. It's akin to predicting their future positions based on their current states and how they interact with one another. For Pluto, this problem suggests that the orbits of Pluto, Neptune, and the Sun work together in an intricate way. Terms like asymptotic libration, scope libration, and VSK wobbling are critical to this puzzle. Astrophysicists believe that the reason all planets maintain their orbits is due to a kind of libration, which in the case of Pluto and Neptune means that when Pluto crosses Neptune's orbit, their positions are separated by about 90 degrees. This distance plays a vital role in preventing their orbits from overlapping and causing a collision. Furthermore, libration refers to the vertical movement of a celestial body within its orbit. For Pluto, this means that when it comes closest to Neptune or any other massive planet, it is positioned far above the plane of their orbit, adding another layer of protection from possible collisions. An additional important aspect in this equation is the VSK wobbling, named after the researchers who first studied how objects move in space. The VSK wobbling refers to the way gravitational forces exerted by Pluto, Neptune, and the Sun influence each other's motion. This interplay of gravitational forces helps maintain Pluto's orbit even when it takes an unconventional path near the Sun. The VSK wobbling is essential in keeping Pluto's orbit stable for incredibly long periods, even when the apparent randomness of the system might suggest otherwise. This phenomenon ensures that despite the seemingly erratic nature of Pluto's orbit, certain forces and patterns help keep everything in check. These gravitational forces and phenomena play a critical role in ensuring Pluto's orbit remains stable, thus preventing potential collisions with Neptune or any other celestial body. The three-body problem is essential for understanding how objects in space interact with each other. It sheds light on Pluto's movement, and helps astronomers understand the gravitational effects on other celestial bodies, including distant stars and planets. Mathematical simulations in the late 1980s revealed that despite the unpredictable features of Pluto's orbit, its path remained stable with only minor deviations in its initial conditions. These features of Pluto's orbit have remained consistent over long periods, allowing astronomers to refine their understanding. Later computer models have also helped us understand how the larger planets, such as Neptune, Jupiter, and Saturn, influence Pluto's orbit. Neptune shares a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps stabilize Pluto's orbit, but Neptune's influence is not the only factor. Jupiter's gravity also plays a vital role in maintaining Pluto's stable orbit, as does Saturn, whose gravitational pull extends throughout the outer reaches of the solar system. Studies suggest that Jupiter's massive gravity is sufficient to ensure Pluto remains on a steady trajectory for an incredibly long period, possibly even billions of years. Together, Neptune, Jupiter, and Saturn may be working in tandem to keep Pluto safely on course, avoiding any disruptions in its orbit. These irregularities in the planetary system play a vital role in maintaining stability within the solar system. Without these forces, our neighborhood in space would be far more unstable, with objects like Pluto potentially colliding with others or being ejected from their orbits, causing chaos among other celestial bodies. Understanding Pluto's orbit is particularly important, especially as there is speculation about a potential collision with Neptune in the distant future. The intricate relationship between Pluto's orbital pattern and Neptune's helps us gain a deeper understanding of how neighboring planetary systems operate and interact. The case of Pluto demonstrates how even in seemingly chaotic orbits, equilibrium can be achieved through the complex interplay of gravitational forces and orbital mechanics. It also highlights the significance of ongoing observation and analysis to manage our place in the universe. Studying the depths of space often forces us to confront the strange and sometimes unpredictable nature of celestial bodies, and Pluto's orbit serves as a perfect example of this unpredictability. The potential for orbital resonance, the critical relationship between Pluto's and Neptune's orbits, is a fundamental aspect of this dynamic. The 2-to-3 orbital resonance ratio between Pluto and Neptune ensures that despite crossing paths, they never collide. This resonance is a crucial piece of the celestial puzzle, preventing any catastrophic interactions. Resonance, where Pluto's orbit is in a 2-to-3 ratio with Neptune's, is a key principle in celestial mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This gravitational resonance helps stabilize their orbits, ensuring that even though their paths cross, they do not collide. This delicate balance is a prime example of how seemingly chaotic systems in space can self-regulate through subtle gravitational forces. In addition to Neptune's influence, other large planets like Jupiter, Saturn, and even Uranus play a role in maintaining the balance within the solar system. Jupiter's immense gravitational pull acts as a safeguard for smaller bodies like Pluto by influencing their orbits and preventing them from being thrown off course. Some scientists speculate that Jupiter's gravity may have even prevented Pluto from being ejected from the solar system entirely. These findings underscore the importance of understanding the gravitational forces at work in our solar system. While Pluto's orbit remains stable for now, there is always the potential for changes in the future. As astrophysicists like Neil deGrasse Tyson continue to explore the universe, they provide us with a deeper understanding of the delicate balance that governs the movements of celestial bodies. The possibility of a Pluto-Neptune collision serves as a reminder of the constantly evolving and complex nature of the universe, illustrating the need for continuous exploration and study of the forces that shape our solar system. This ongoing study of Pluto's orbit and its interactions with other celestial bodies is not only important for understanding our solar system but also for exploring the broader universe. As scientists like Neil deGrasse Tyson continue to examine the dynamics of space, they highlight the evolving nature of celestial mechanics and the complexities involved in predicting the future movements of planets and other objects. The possibility of a Pluto-Neptune collision, while unlikely, is a reminder that the universe is filled with uncertainties, and even the most stable systems can undergo profound changes over time. Moreover, Pluto's case exemplifies the intricacies of orbital resonance, where the movements of celestial bodies are intricately linked. The 2 to 3 orbital resonance between Pluto and Neptune ensures that despite the crossing of their paths, a collision is avoided. This resonance is a direct result of the gravitational interactions between the two bodies, creating a delicate balance that has kept Pluto's orbit stable for billions of years. It is a prime example of how gravitational forces, even in seemingly chaotic systems, can produce stable and predictable outcomes over long periods. The significance of this resonance cannot be overstated. It serves as a fundamental principle in celestial mechanics, demonstrating how even the most complex and irregular orbital patterns can maintain harmony through subtle gravitational influences. This understanding of resonance also extends to the broader dynamics of the solar system, where the interplay between planets, dwarf planets, and other objects is crucial to maintaining the stability of the system. Jupiter, in particular, plays a pivotal role in the overall stability of the solar system. Its immense gravitational pull acts as a protector of smaller objects like Pluto, helping to prevent them from being flung out of orbit or into catastrophic collisions with other bodies. The gravitational influence of Jupiter extends well beyond Pluto, impacting the orbits of asteroids, comets, and other small bodies in the outer solar system. This further highlights the interconnection of the various objects in our solar system and how their gravitational forces work together to maintain order and balance. In fact, some researchers suggest that Jupiter's gravitational influence may have played a role in ensuring that Pluto remained in its current orbit rather than being ejected from the solar system entirely. Jupiter's gravity may have helped capture Pluto, preventing it from being sent off into interstellar space. This scenario underscores the importance of understanding the role of each planet in shaping the overall structure and dynamics of the solar system. The study of Pluto's orbit and its interactions with other planets also highlights the dynamic nature of space. While mathematical simulations and computer models provide valuable insights into the behavior of celestial bodies, they also reveal the inherent uncertainties in predicting the long-term movements of these objects. Small changes in initial conditions or minor deviations in gravitational forces can lead to vastly different outcomes over time. This uncertainty is a reminder of the complexity and unpredictability of space, and the need for continuous observation and analysis to refine our understanding of the forces that govern the universe. In the broader context of space exploration, Pluto's orbit provides valuable lessons about the intricate balance of forces that shape the behavior of celestial bodies. The fact that Pluto's orbit has remained stable for billions of years, despite its erratic and unusual characteristics, speaks to the power of gravitational forces and the self-regulating nature of orbital mechanics. It also underscores the importance of ongoing research and the need to continuously refine our models of how planets and other objects move through space. As we continue to investigate Pluto's orbital dynamics and its relationship with Neptune, it becomes increasingly clear that the balance of gravitational forces is not as simple as it might first appear. For many years, Pluto's orbit was seen as a curious anomaly, its eccentricity and inclination setting it apart from the other planets in the solar system. This has led to significant interest in its interactions with Neptune, as well as in the broader questions of how other bodies in the outer solar system behave. One of the key aspects of Pluto's orbit that demands attention is its resonance with Neptune. The two bodies follow a 2:3 orbital resonance, meaning that for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This resonance locks their orbits into a stable pattern and effectively prevents a collision, even though their orbits cross each other. The gravitational forces between the two bodies are finely tuned, with the positions of Pluto and Neptune always remaining in a synchronized rhythm. This delicate balance ensures that the two bodies never occupy the same position at the same time in their respective orbits, even when they are closest to one another. While this resonance helps prevent an actual collision, the interaction between Pluto and Neptune also raises larger questions about how planetary bodies interact in our solar system. For instance, there are other dwarf planets, comets, and asteroids in the Kuiper Belt and Oort cloud, which are regions that extend far beyond the orbit of Neptune. Many of these objects, too, are subject to the gravitational forces of Neptune, and understanding the interactions between them helps astronomers make predictions about potential future disruptions to their orbits. Additionally, there is growing interest in the possibility that our solar system may not be as stable as it seems. As the planets orbit the Sun, their positions and gravitational effects on each other can lead to slow shifts in their orbits over time. While the gravitational interactions between Jupiter, Saturn, and Neptune have kept Pluto's orbit relatively stable, there is always the potential for perturbations from other sources, such as nearby stars or passing celestial objects. These events could alter the orbits of bodies in the outer solar system, including Pluto, in ways that might not be predictable based on current models. Recent research into the outer solar system has also pointed to the idea that Pluto's orbit might not have always been so stable. Some scientists theorize that Pluto could have been displaced from its original orbit at some point in the distant past, possibly due to gravitational interactions with other large bodies or a cataclysmic event that changed the structure of the solar system. While this is speculative, it adds another layer of intrigue to the question of how stable Pluto's current orbit really is, and whether we are witnessing a temporary state in the system's long-term evolution. Moreover, studying Pluto's orbital behavior also highlights how our understanding of planetary mechanics continues to evolve. With the advent of more powerful telescopes, advanced computer simulations, and space missions like NASA's New Horizons, scientists are gaining more insight into the dynamics of distant objects. These tools allow for more precise measurements of Pluto's path, and enable astronomers to refine their models of how such bodies interact within the broader framework of the solar system. This ongoing research on Pluto serves as a reminder that the universe is full of mysteries, and that even the most seemingly predictable systems can hold surprises. While the potential for a collision with Neptune seems remote, the possibility underscores the intricate, often precarious nature of celestial mechanics, offering us a deeper appreciation for the forces that govern the cosmos.